Good afternoon. It's great to welcome Jamie to give a talk and theory seminar. Jamie Morgenstern, who is from University of Washington. And she is, we're very happy to have her, and she'll be talking about a smooth analysis of the greedy algorithm for linear contextual bandits.
Okay, thanks, Anna. And I think I've given talks in the theory lunch, but maybe never the theory seminar. I'd have to go back and look at my notes, which are probably far from perfect. At some point, you will get old enough that you've had several email addresses, and you'd have to like check several email accounts to remember where exactly you gave talks. And anyway, I guess I've reached that point. Right, so I'm going to give a talk today, which I don't think will take the whole hour, and I'm happy to spend some time talking about some of the details of this work rather than like plowing through 50 slides. I think there are only 25 slides or something. But this work is in this domain of understanding when we can give theoretical guarantees for algorithms in settings where the instances they're looking at are neither super, super nice nor super, super difficult, right? So, the meta question that this work aimed to begin to understand is when and why greedy algorithms work well for bandit problems. If you know what that means, great. If not, I'm going to give you a bunch more details in a minute. Okay? But this is just sort of like the driving question, right? So we're all in theory seminar, so I'm going to give you one slide that you'll all be bored with, but I apologize. This is just like a slide that I like to make. Okay, so classic algorithm design, like offline batch algorithm design, generally assumes that we have some fixed input, right? And all of it is given to our algorithm at once. And it's easy to measure, like fixing a valid solution for that input, the objective value of that fixed solution. Okay? It may be complicated to find a valid solution. It may be complicated to find a valid solution which actually optimizes that objective. But in general, the paradigm is we have all this information at once in classic algorithm design in this like offline batch setting, right? Okay. So in general, barring computational concerns, the goal here is to find a valid solution for this input, which optimizes the objective function for the input, right? And the input can, in general, both affect what the objective function is, and then also what the feasible set of solutions can be for a given problem, right? That's what an instance looks like in classic batch offline algorithm design, right? Okay. So you guys have all been coming to these theory seminars for a while. I would imagine that this next slide is maybe not so much of a departure for you. But online algorithms in general assume something a little bit different, right? In general, this batched fixed input assumption is generally disposed of, right? And the assumption is then that your input arrives sort of piece by piece. And as each piece arrives, you have to make some decision to serve that piece, right? The classical example, which many of you have probably seen, is paging or caching, right? And so when someone requests a page on Google, they can't wait for 6 months and then do some fancy optimization for what they keep in cache. They have to decide how to serve that page right now, right? And maybe they'll kick something out of some local cache that they would have wished to, in 30 seconds, they'll be asked to serve that again, and they would have liked to have kicked out something else had they known the future, right? And in general, the assumption when we're thinking about online algorithms is that these sequences will generally be built to make our algorithms look as stupid as possible, right? I'm grossly overgeneralizing, but like, much of online algorithm design and looking at competitive ratios for problems such as caching or K-server or things like that generally assume that like the input and the algorithm are being designed in such a way to like make the algorithm look really terrible, right? Okay. So the choices that an algorithm makes in these settings generally sort of have two consequences, right? One of which has something to do with the reward or optimality of the choice just for serving today, right? For example, when I serve someone a page from cache versus a page from main memory, those will have different costs. I assume some of you actually know some of the words that I'm saying. How many of you, anyway, it's fine. I don't know anything about caching, so like if I make a mistake, this is why. But you have some cost that you incur today, which is part of the cost of the cumulative algorithm design process that you have, but also you have some state. And when you decide how to serve this page today, depending upon which of the pages you kicked out of your cache to serve this request, you now have a different state, and going forward, your cost to serve future requests has changed from what you had today, okay? So in general, when you're trying to decide how you want to make a choice today, it's not enough just to consider what the objective value is for different choices you could make today. It's also worth considering what things you'll observe in the future and sort of how choices you make that affect the state will change your objective value longer term. Okay? I don't think this is a particularly complex deviation. I just want to be very precise about this. Yeah?
But how can you optimize today for something that you don't know what's going to happen in the future?
Right. So in general, it's very difficult, right? And what I mean by optimizing will depend on precisely how I define everything. Right, so competitive ratio in general looks at like if you knew the whole sequence in advance up front, make a fixed choice, right? And sometimes you can compete with that, sometimes you can't. Sometimes you can compete with more complex policies, sometimes you can't. Okay, great.
So you talk about optimizing when you don't know what's going to happen, but you don't know the probability distribution of what might happen.
You may have information about the probability distribution. You may sort of be much of online algorithm design doesn't even assume that your future examples or your future choices are being drawn from some distribution. It's just that they're being designed to make your competitive ratio as high as possible, right? Which is way more negative in some sense than like what I'll talk about for a moment in coming up, which is thinking about machine learning algorithms, right? I think one of the key distinctions between thinking about like machine learning and thinking about algorithms is fundamentally a question of how much randomness you want to assume the instances you're observing have, right? That's from my takeaway, that's like the primary distinction, right? So I didn't change very much here. I changed a couple of the pictures and I added one piece of information here. Okay, so for online machine learning algorithms, right? Again, there's this idea that we're getting pieces of our input bit by bit for which we have to make decisions. And we have to make those decisions not knowing what's going to happen in the future. But as was asked before, right, it may be the case that we actually learn something from the decisions we're making today, or the information we're seeing, the pieces of the information we're seeing today about what we might observe in the future. Okay? So primarily, the one distinction between the last slide, which was online algorithms and online machine learning algorithms, is that there may be some information that ties these different rounds together, right? Perhaps the simplest example is like, okay, I'm going to make a bunch of choices for independent draws from the same distribution, and I'm going to have to label them over and over again, right? There may be much more complex things, but okay, great. Okay, so the question that this work aimed to understand, or that online machine learning algorithm design tends to want to understand, is the following. Suppose I have some information about previous choices I've made, sort of how well they've treated me in terms of the optimization I've been doing. How should I behave today for this next bit of the input sequence, right? In particular, when this is not the last day, right? I'm not just trying to optimize my objective function today, but I actually care about some long-term objective function over all the choices I make. Okay. Does this make sense? I don't think I've said anything too complicated. I've tried not to have any math on the slide so far. Okay. Okay. So I am going to say a little bit about the model that we think about in this paper, and we'll see if anybody has some pushback on it. I think there may be. So like I plan to spend some time on these slides. Okay. So this work thinks about how many people have heard of multi-arm bandits? Okay, sweet. Cool. All right, so I'm going to give you two stylized models of multi-arm bandits. I will present them to you on these slides, and you can take them or leave them, but like they in general are sort of thought of as equivalent, but they'll be different for this set of results, and you'll see why. Okay, so the first one we call the single parameter model. Right? So in general, when we're talking about multi-armed bandits, the assumption is we have some selection of choices that we have today. We have some information about those choices, and then there's, in the linear case, there's a single linear function that's governing the reward for choosing any of those different contexts. And the reward is just that linear function multiplied by the context of the thing we choose, right? So in general, the assumption is that sort of a priori, before anything happens, the adversary selects some d-dimensional feature vector. I'm putting the green box around as though this is something that the algorithm does not know. Okay. And then on each day, right, for some large number of rounds, the assumption is that the adversary picks k different contexts, right? And you can think of these as like, if you're thinking about selling ads, you can think about these as examples of the different cookies people might have in their caches. You may think about this as like some medical history for different people. There are all sorts of different things you might encode in these contexts. The algorithm then picks some number between 1 and k, which corresponds to them saying, I think IT is going to be the action I want to take today, right? And they observe some reward, which is superscripted by t and subscripted by it, because it depends on the choice that the algorithm makes and also on round t. Okay? And the assumption is that the expectation of that reward is equal to the dot product of this unknown parameter vector theta and the context that the algorithm actually did see. Okay? Good.
You have no notion of what the actual distribution is. You only know the mean.
Yeah. So we don't even know the mean.
I mean, sorry. I mean,
sure.
Theta,
Sure. You know.
Theta only like the
Right.
adversary.
Right. The adversary. Sure.
Only knows.
So the adversary could also be designing these distributions. The statements I'll make in a couple of minutes apply for distributions that satisfy a couple of nice properties. Okay, but yeah, in general, you can imagine the adversary doing all sorts of nasty things right here. Right? Yeah.
The distributions you're talking about is the error distribution on R,
or the noise distribution on R, sort of how R is distributed. Yeah.
Yeah, not the X's, which are assumed to be like.
That's right.
Right.
That's right.
No distribution.
Right. So far, what I've assumed is that the adversary selects them in an arbitrary fashion. There was another question over here. Yeah.
It's about the same thing, so I just didn't understand the model. So what is the distribution and what is the power? What is the expectation over?
Sure. So the expectation is only going to be over the draw of the reward, which the reward is going to be drawn from a distribution that has the right mean, and you can imagine it has like finite many moments. You can assume it's bounded between 0 and 1. There are slightly different variants that make more sense for different problems.
So this distribution is chosen by the adversary,
Mm-hmm.
and it can, besides this, be arbitrary.
So
Besides this condition that's written in the green box.
For this slide, yes.
For this slide, yes. Yeah. So there may, and in many cases there are lots of assumptions where like, this has to be normally distributed or sub-Gaussian or bounded between 0 and 1, right? As James mentioned, like lots and lots of results depend sort of delicately on what that distribution looks like. The couple of results I'll mention don't assume all that much about that distribution other than something that sort of, I don't even know how to decouple exactly what it says about that distribution, but it does imply something there. Yeah.
So the choice of the IT depends on what? So what can I see when I click IT?
So the algorithm sees xt1 through xtk. It sees the rewards of the previous actions it selected, but not the rewards of other things. And it doesn't know theta, which is why it's in a green box. Okay? It also doesn't know the distribution that these are being drawn from. Okay?
Can depend on IT or no?
The distribution will depend on IT in the sense that it has a mean that depends on IT. Yeah?
Oh, okay.
Okay. Other questions? Okay, good. I know that this is like it's a pretty standard model, but I'm being pretty pedantic for a couple of reasons that are sort of unfortunate for this particular work. Okay. All right, so I want to present two, right? Like you'll notice that I call this the single parameter model. I wouldn't have given it a name if I was only going to have one. Okay, so I've now changed the top of the slide to say multi-parameter model, and I'm going to, all the stuff on there so far is still the same, but I erased a couple things and I'm going to replace them, okay? So now I want to imagine that the adversary, rather than selecting a single set of d real numbers, is going to actually select d times k many, okay? So this is going to correspond to me having k actions, and each of those actions having a different linear function governing the reward for selecting that action as a function of the context on that day. Some people are saying yes, some people are looking blankly. Okay, so a simple example here is, suppose I'm choosing, I can choose to provide any person, I can choose to provide Thomas an ad for Nikes or myself an ad for a new iPhone, but I don't get to choose sort of how I assign the ad to the different advertisee, right? So I know a bunch of information about my individuals, and I don't know sort of the function that maps those individuals, the information about those individuals to rewards, but I understand they're sort of tied together in this nice linear way. And that those linear functions might be different because Nikes behave differently according to the cookies that Thomas has than iPhones do. Okay. So I have one more thing I have to give you, right? Also, we'll assume that the adversary picks those and that the algorithm doesn't get to see them. And the one difference that I wrote here, right? This is almost the same, except for when we're looking at the expected reward for the algorithm. That expected reward is now the inner product between the linear function for the action that algorithm chose and the context for the action the algorithm chose, right? I just added one annoying subscript. Questions? Okay, right.
So the k for theta and the k for x does not necessarily need to be the same?
So I'm assuming they are the same. So you notice these are matching, these subscripts. So you choose some number between 1 and k, and that corresponds to saying, I like this context for this same action, right? It's not a matching, which would be like a different and also interesting but hard problem, right? So this is sort of saying I'm given k choices, like maybe I have $1 to spend on advertisement and I can spend it in one of k ways, but I can't put an arbitrary ad in front of an arbitrary person. I just have like an ad I can show or not to one of k people, and they have different information. Okay.
I think you already answered it before, but so if the adversary chooses the same xi in different rounds, I only have the same guaranteed expectation. Like, so the distributions will be completely different.
Yes.
There's no guarantee.
Yep. Yeah. So far, I have made no distributional assumptions, and that was intentional. Okay, so yeah.
Why do people like consider
Linear functions?
functions? Yeah.
So there are a couple of reasons. One of which is that we understand linear functions a lot better than others, and there are more like nuanced reasons that we could talk about offline. I think in general there's a question of the right way to measure how well we've learned a function, not in linear space, right? So, okay. So in general, I think these are just like two very mild variants of like a problem you guys have probably, like almost everybody, maybe everybody raised their hand. The only, and they're sort of, if you squint at them correctly, they're almost the same, right? Like you can sort of embed one in the other. And in general, like that's why this distinction is not made, right? In general, we think of like a single linear function and like maybe k different contexts, and you can sort of embed k different contexts into k times d many dimensions. But for a particular reason that maybe you'll see when we get to it in a couple of minutes, these are not the same for this particular talk in terms of what they'll imply. Okay, so since you guys have all heard of multi-arm bandit, I'm going to assume that you guys have heard of regret. I think that's like slide 3 or 4 of most things about multi-arm bandits. So an algorithm is said to have regret R of t if, when you think about a policy class pi, which I'll get back to in a second, for any sequence of feature vectors, if you look at the total reward of the best choices with respect to pi, I'll get back to that in a second, and the expected total reward of A, that difference shouldn't be more than R of t. Okay? So I want to get back to this pi, right? So in general, if we allowed the baseline we were comparing ourselves against to depend arbitrarily on all of the contexts that we saw, this thing would look like opt, right? Assuming that like we didn't see repeats of the same exact contexts, right? So in general, there's some assumption that like we're going to limit the strength of the benchmark we're comparing ourselves against, such that, for example, maybe we're only making choices that do really simple things with respect to the current set of contexts and decide which of the k things to choose based on some relatively simple function of the current k context. It looked like somebody had a question. Did I miss it? Okay. All right. So I still think somebody had a question. Okay. So this thing is sort of somehow constraining opt, right, by saying like I'm only going to allow the selection of 1 through k to have some particular form. And in general, what we hope is to be able to say that R of t can be sublinear in t, right? So this just means that like as t grows, as our algorithm plays for longer and longer, it is getting closer and closer in some average case sense to the best thing you could do had you known all the information up front, but you were still constrained to make a selection between 1 and k from this policy class pi. Okay? Yeah.
So now this definition, right, so consider these vectors of the feature vectors to be non-adaptively fixed, right? Does it make sense to consider a setting where the adversary plays adaptively against the algorithm? Or?
Yeah, so it does. I'm going to elide questions of adaptivity versus non-adaptivity for the purposes of this talk. But yes, there are interesting questions there. Okay. Other thoughts? Okay. So I'm going to do this, but you don't have to parse it. Okay, so this is just saying like what the functional form of the expected reward of the best choice in pi, where pi is just allowed to look at the current set of contexts, compared to the reward that I would see for my choice, right? If this were the multi-parameter setting. Okay. Okay. So I want to make a small distinction, one more small distinction, which is often not made in regret minimization, but it's useful to make sometimes. So suppose we have an algorithm, and we want to say that it has regret R of t, but like not with respect to any arbitrary sequence it could see, but with respect to some nice data generating processes. Okay? So this is sort of in between the like algorithm design, things could be arbitrarily poor, and like IID, everything's perfectly nice. Maybe there's some class of data generating sequences that we'll actually be able to say we have good regret with respect to, and then argue that maybe sometimes we're in that space. Okay? So I want to think about, and I didn't use, this is new notation, so if there's a problem with it, let me know. Let's imagine we have a sequence generator M, okay? And this sequence generator is actually going to generate all of my, actually I want this to be x1 through x capital T and ignore the lower subscripts, okay? So I want to imagine that my sequence generator is thinking about all of time, and it's going to generate these sequences, or it's going to generate all of the context I'll observe and decide based, and we'll actually measure our regret with respect to like something about the expectation with respect to M, okay? So the regret I'll define in exactly the same way as I did before, only I will want to assume, this used to say for all sequences of feature vectors, and now I want to assume only that the sequence of feature vectors I see is drawn according to this nice sequence generator, okay? Yep.
So you briefly revealed on the previous slide what pi was,
Yeah.
and pi looked like the expert setting as far, and you were sort of comparing the regret of bandits versus experts. Is that a?
So I don't think that's what I was doing. I'd have to think a little more closely about it.
You just get to look at
Today's contexts.
Today. Oh, yeah.
Yeah.
Oh, so it's even weaker. Okay.
Yeah.
It's even weaker. You didn't get to look at.
Sure. So like I'm not really playing with pi, so I'm not being very particular about it. But what I'm thinking about in general is I want to constrain my benchmark to like not do crazy clever stuff, right? And by not do crazy clever stuff, in particular, I don't want it to contain a function that would allow it to choose the optimal thing for every day if it was given unique combinations of contexts. Okay. Is there any other questions? Okay. Okay, good. Okay, so the question that I sort of want to ask, or this work looked at, is what properties of M, this sort of data generating process, make regret minimization easier? Okay? So like what property between different rounds might make this a particularly nice problem or a particularly not so nice problem? Okay, so this is sort of like high level, if you had never heard a talk about exploration and exploitation before, right? So if you're doing regret minimization, there are generally like two types of behavior you're doing in any given round, or maybe some round is some like nice mixture of the two. Algorithms for regret minimization are usually either doing something called exploration or exploitation, right? So exploration is a stage in which the algorithm's hoping to learn something from the choice it made, but doesn't actually think that that's necessarily the best thing to do for today's reward, okay? So you could imagine, oh, I've never seen someone like Thomas react to a Nike ad before. I don't think he's going to click on the Nike ad, but I'd like to see something about like how lots of Thomases or how some fraction of Thomases respond to this ad, because like maybe there's some chance he really likes Nikes and he's willing to spend $400 on them or something, okay? Exploitation, on the other hand, is just the opposite, right? It's sort of pretending that today is the last day, and I don't care about the value of information that I get from today. I just want to sort of earn as much money today as possible, right? And most regret minimization algorithms sort of either subtly or not so subtly go back and forth between these types of things. And when I say greedy, and I've said greedy a couple of times, what I generally mean is only doing exploitation. Right? Sort of ignoring the fact that we have imperfect information, ignoring the fact that there are a bunch of days in the future that we sort of would like to reason about and think about in terms of the amount of uncertainty we have. Just do the thing that's right for day little t on day t. Okay? And in general, that doesn't have great performance in a lot of these settings, right? Just because it's right for like the, having 1 day left doesn't mean it's going to be particularly good for more than 1 day left. Okay? Questions? So we aren't the first people to ask a question somewhat like this. So I'm going to tell you a small, I'll give you like a very informal version of someone else's theorem, and then I will show you how our theorem is somewhat different from this. Okay? So in a very elegant paper from 2017, a very similar question was asked. So the theorem says if there are only two actions, okay, and the context distribution satisfies some property that I'll get back to, greedy will be no regret. Okay? Does that make sense? If I don't say anything else for a moment, ignoring what f is. Okay, so I told you in general greedy is not going to be no regret. If I constrain what the data generating processes are that greedy faces, sometimes it can be no regret with respect to those data generating processes. Okay? So what precisely is this property that the data generating processes have to satisfy? It has something to do with how much you learn when you make a choice according to greedy. So in general, when I decide, okay, this thing looks like it will be best for my reward today, it also better be the case that I'm learning something new about something I didn't know before with some probability. I'm seeing some nodding heads. Okay, so in general, if we're thinking about linear functions, think about like everything being nice and round in all of our dimensions, right? Sort of no matter what hyperplane we're on one side of, there's a reasonably good chance I'll get some variation in all my different dimensions. So I'll basically constantly be learning about the functions or the function that I don't know everything about, regardless of like how I make that choice. Okay? Okay. I put a star here because one of the implications of this particular version of assuming spread assumes that I have two actions, and each of them will be the best with constant probability. Okay? So this is one of these. This is a sort of strange thing. Let's think about what this means for a second. If we're in a setting where we're choosing between two things, and they're both pretty good most of the time, right? If there's enough variation in my context distribution, then greedy will be no regret. Okay. Okay. So this is prior work, which is really elegant, and I highly recommend reading this paper, especially if you're sort of thinking about greedy algorithms in an online setting. Let me tell you sort of the high-level takeaway of the two theorems in our paper, which are a little bit different. And in particular, they don't, the assumptions we make on the context distribution don't imply that, if I'm given k actions, each one of them has probability something like 1 over k of being best. Okay, so we'll start with the single parameter regime. Okay, so the single parameter regime, remember this is just that on day t, there are k different contexts, right? Those each correspond to a person, but there's a single linear function that's governing the reward no matter which of the k things I select. And just the ith context will be the one that takes the dot product with this fixed parameter to give my reward on that day. Okay, so the theorem in this setting is that if there's enough diversity in the context that greedy selects, then greedy will be no regret. This is actually like square root t, okay, something reasonable, not like t to the 9/10 or something. Okay. Okay. So this is a little bit different than what the previous slide had, right? First of all, it works for an arbitrary number of different actions, right? It's not sort of constrained to only be considering selecting the better of two actions. And that's sort of important in terms of like the geometry of the decision space, amongst other things. This diversity assumption is also somewhat different than the covariate shift they assume, okay? I'll tell you a little bit more about this in a minute. I want to tell you sort of, we need like one more assumption to get some guarantee for the multi-parameter regime, and then I'll talk you briefly through those two different ones, okay? Okay, so in the multi-parameter regime, we need something else. We also will need this sort of having some diversity, right? So if there's enough diversity in the contexts that greedy selects, and when a given action is best, there's a reasonable probability it's best by some margin, then greedy with a relatively small warm start will be no regret. Okay, so a couple of things. Greedy with a warm start, what the hell is that? I just like gave that to you on this slide and I didn't mention it, right? So I want to imagine that each of my different k arms, I have some uniform random samples from them from the beginning, right, that are maybe drawn from a distribution that has some nice properties, okay? The size of that warm start will be relatively small and not depend on t, okay? So this is like a much smaller warm start than you would normally need to argue about something like, epsilon greedy or something, okay? The second thing, when I is best, there's a good chance it's best by a margin. What on earth could that mean, right? So does anybody have some intuition for why such a property might be nice if we're doing learning?
Well, if you've got two things that are really close to each other, you're going to continually get the loss of their difference at every step. You're never going to be able to get a little of
Yeah, that's right. Right? Okay, so in general, when you have two things that are really close together in terms of their reward, you have to, at some point, distinguish between them, or you'll basically constantly be suffering their difference, okay? And so, a bunch of regret minimization sort of the regret guarantees have like two forms. One depends on t, but is independent of all other parameters of the problem, and the other one sort of depends on this capital delta, right, which is often the gap between the best and second best actions rewards or something like this, right? That's where this comes from. Basically, being able to distinguish between two things that are close together is kind of hard from samples. Okay. So I want to tell you a little bit, I will tell you a little bit more about this diversity property and also this like best by some margin property. But I want to change the perspective of precisely how these contexts come to be before I do that. Okay? So previously I was imagining the adversary was selecting contexts, right? And those were going straight to the algorithm, and the algorithm was having to choose its actions based on those. And then I said something about data generating processes and didn't really say very much after that. And I just said like maybe if the adversary or the process that generates my context is constrained in some way, there will be something nicer that we can say about certain kinds of algorithms. So let me give you a slightly more formal version of the sorts of data generating processes we were hoping to capture. So suppose we have an adversary selecting contexts, right? And these are all of the contextual information we'll need from day 1 through day t for all of my k different actions. And nature perturbs them, okay? So nature takes some like random noise and just adds it to each of the different contexts, independently for the different days t. Okay? So this is something that is probably starting to feel a lot like, follow the perturbed leader or something, right? We've got like sort of the adversarial sequence. There's some like nice randomness that's being added to it at the end, and then the algorithm's actually going to face this sort of slightly perturbed adversarial sequence. Okay. So then assume the problem is defined with respect to the perturbed contexts and not the adversarial ones. I'm seeing some nodding heads and I'm seeing some not so nodding heads. Does anybody have a question about this? Okay, so why are these important? Why did I ever begin with an adversary if I was going to replace it with something else? The first answer that I could give you is that like I do want to allow that, and the whole reason we think about online algorithms is that things are generally not static, right? I want to imagine that the instances I'm seeing over time are changing with respect to time. Maybe not in a way that's sort of adversarially done against my algorithm, but maybe, right? Why am I thinking about some perturbation here, right? And the reason I'm thinking about a perturbation here has something to do with what Paul said, and something just generally to do with like things that are very close together tend to be really hard for algorithm design, right? So like ties, I don't know how many papers I had like early on in grad school where like tie breaking was the thing that took like the longest out of all of the stuff to write the paper. Tie breaking is like really bad when it comes to voting or mechanism design, all of these things, they like come up a lot, right? So thinking about slightly perturbing all of the context sort of breaks a bunch of maybe noxious ties, maybe, right, is the hope. So this is some model where we have contexts that are allowed to change over time, the distribution's allowed to change over time, but they're not allowed to be constructed quite so nefariously as like an arbitrary adversary sequence. Okay, so if this is the assumption that we make, that this is where the context we're actually observing in the previous slides were coming from, then basically all we need to know is what properties of D would make greedy no regret, okay? Because the adversary, I'm still letting it do whatever it wants for these sequences before I perturb them. Okay, so I have two things I have to define for you, one of which has to do with this diversity property, and the other has to do with this margin property. All right, so let's start by thinking about diversity. And I'll say this distribution where sort of the perturbations are coming from is R lambda diverse. And the intuition behind this, again, is like no matter what greedy knows right now, conditioned on it picking something that it thinks is best, it's going to learn something. So this should have something to do with the minimum eigenvalue above some linear threshold. So that's what this is. I'm not suggesting you necessarily need to parse this thing. I'm just saying that, like, if you go through and you think about how greedy will behave, and you want to sort of argue that sort of no matter what information greedy has so far, greedy is going to continue to gain more information, it's helpful to think about greedy having some current linear threshold in its head. It's picking something which it believes is above that, and then that it should still have some reasonable minimum eigenvalue above that. So you're still learning something in all directions. Okay? Okay. Oh no,
Yeah.
don't parse it. Yeah.
So the mu there is, so what type is that? Is it a random variable too? Or is it
So I think mu should actually be x hat, x tilde, yeah. Okay, you really don't have to parse this. I am happy to explain any piece of it. I'm just saying here that, like, we're looking at these perturbed contexts, and we want some property of the perturbed context in so much as we want them to be kind of high enough dimensional that we're always learning from them when we see observations, even when we're selecting. Like, this might be true for lots of distributions if you don't do any conditioning, but the thing that makes this complicated is greedy is making some choice as a function of the contexts, which thing it thinks has the highest reward, and then its feedback is also a function of those same contexts. So if you're trying to argue that it has sort of IID observations, that's simply not true. Okay, so the other property, which we needed at least for this multi-parameter regime, was something about margins. And I guess I can, like, give you the same kind of, like, flash through, but, like, I think it's very similar in this idea that, like, if things are really similar, I'm going to be in trouble. So I want, if something's best, for it to be best by some margin with some reasonable probability, which will then imply I pick it with some probability and I learn from it. Or if it always sucks, but it always sucks by enough of a margin, I don't have to learn about it, right? So this is one thing that fundamentally distinguishes this from, like, prior work that's been trying to understand greedy algorithms. We don't need to assume that all of the actions are pretty good some of the time, right? And that's something that comes up sometimes in regret minimization. It's like, well, if all your actions are pretty good some of the time, maybe, like, random, doing some random stuff for a while is, like, pretty okay at the beginning. Okay. So we'll say the same distribution over noise has margins, R, alpha, gamma, which, again, you don't need to parse this. This is just, like, telling you a little bit more formally about what I mean. If something is best, it's best by some margin. So this B is the margin with some probability gamma. Okay. So again, this is supposed to be an x tilde. Okay. This is just, again, saying, like, if I think a context is going to give me the best reward, it better be the case that it's actually best by some margin with some probability, so I actually pick it with some probability. Okay, so the main, this is not the way, like, the paper primarily pitches itself. This paper primarily says, okay, we're thinking about the linear contextual bandits problem. Imagine it's slightly perturbed. Then we get regret for the greedy algorithm, right? We get, like, a no regret algorithm out of the greedy algorithm, and greedy is almost never no regret, right? So why did we ask this question to begin with? And I have a couple of answers for you. One of which is that there's a bunch of empirical work that shows in these sort of settings where contexts are changing, like online advertising and other things, that greedy often outcompetes the no regret algorithms we built. Which, for better or worse, that seems to be something that we observe a lot in practice in lots of online settings. And, like, Microsoft, there are a bunch of papers out of the MSR New York lab that have some really elegant observations of this variety. So that's one of the reasons we were interested in this work. The other is that this sort of fits in a nicer, large picture of understanding when algorithm design is difficult because of, like, small parameters that you can, like, manipulate a little bit, and suddenly the problem becomes much easier, right? In combinatorial algorithm design, this doesn't make as much sense, right? But like when you have continuous functions and there are lots of ties, like slightly breaking the ties in an arbitrary way, suddenly making the problem much easier, maybe suggests that like real numbers are sort of getting in our way rather than helping us. Okay, the other reason, that's the wrong slide, hold on. Okay, there we go. wrong order. Okay, so why might people want to use a greedy algorithm, right? For one, as I mentioned, like there is some evidence in some of these dynamic environments that they actually outperform no regret algorithms in terms of their cumulative reward. Another reason is the following. Suppose what I'm doing is actually not like providing Nike or iPhone advertisements, but I'm actually making choices about how to treat different kinds of patients with different kinds of interventions for a given illness. All of a sudden, exploration and exploitation seem to have really different values to the people who are participating, right? Rather than just saying, oh, I'm seeing an ad for an iPhone or an ad for Nikes, I'm either being given something which may be suspected to be a placebo for me for the kind of illness I have, or something that is probably the better treatment for me to get well from some illness I have, right? So this was actually the Bastani et al. Motivation for thinking about greedy algorithms. Like, when is it the case that we can make good choices for individuals in some system and still guarantee that the system, over the long run, actually learns enough to make good long-term choices? Okay. Okay. So I think that's all I wanted to say. I wanted to give people lots of time, and I'm happy to stick around and answer some more technical questions. Thanks. Paul looks like he's thinking about a question.
It's just about this relationship between what you're doing and sort of smooth analysis with classical algorithms. And it sort of feels, you've got multiple different things, because you're both changing the policies you're
Comparing
against and and your algorithms. I mean, it seems plausible that you could just do the comparisons under a smooth analysis model and do a high I would alone. I mean, type model where you're comparing to opt.
Mm-hmm.
But I mean, that would be sort of the first classical first step of doing smooth analysis and on.
Yeah.
And I wonder where that is in between what you're doing. And
that's a good question, and that would be something I'd have to think a little bit about. My guess is that won't save you from some of the sort of pathological examples. The reason being that this random tie breaking. So the problem with comparing to opt. This is, I think Paul's pointing out this like weird thing about pi that I didn't spend very much time talking about. This policy that's choosing the actions that I'm comparing to and using as a benchmark. So the reason I had that there, and I sort of said a little bit about it and waved my hands, was that if we assume that all of our days are distinct in context space, meaning like every day looks a little different from every other day, opt could, in theory, pick exactly the right thing every day, and we're going to be in big trouble when comparing to that, right? Certainly for additive regret, and maybe even for multiplicative guarantees. And I don't think that gets better when you add a little bit of noise. So, yeah. Other questions? Yeah.
Can you give an example of like when this margin would be like useful? Like what would break?
What would break if you don't have this margin, or what like? So.
Because the error distribution is fixed, right? The noise distribution.
So I'm imagining that the noise distribution has some properties, right? Including that it has this like margin property. So I think the reason that this sort of falls out naturally of thinking about like how can I make sure that like if something's best it's best by some margin, so I learn from it, right, from the other piece, right? It doesn't always apply if things are really close together in terms of true reward. Expected reward.
But the expected reward is just a linear.
So the problem is that the expected reward is a linear product of something that includes this randomness. So,
I guess the randomness isn't changing over time, right? It's not like you've got some weird.
so the randomness is changing over time in the sense that each day has an IID draw.
Right, but it's not the distribution.
The distribution was not assumed to be changing over time. So I think the concern, I may be misunderstanding what you're asking, so I should probably ask offline. But the primary issue with like thinking only about expectations is still when stuff is pretty close. So like the reason these margins help you is when stuff is pretty close before the perturbations like one of the corollaries of this is that like if you take a contextual bandits problem and you add IID random noise to each of the coordinates for each of the arms drawn from a Gaussian with sufficiently widespread, then like greedy will be no regret in that setting. And I'm not totally sure. I think I maybe don't understand your question, so maybe we should chat about it offline. Other questions?
Okay, thank you.